Good afternoon, friends. So, in this lecture we have seen what is a differentiable function in differential geometry. What is a differentiable function? We have defined one mapping x from D to M, and what is f? F is a real valued function defined on M. That is, f is a real valued function defined on M means what? The codomain is R, and the whatever the domain is a whole surface M, and x is a function from D to M is a coordinate patch. It is given to us. Okay, as it is a coordinate patch, it means that it will satisfy the condition of 1 and regularity. Okay. Next, then the composite function f of x or f composite x is a coordinate expression for f. Then f is a real valued function. F of x. That means you have to now find out a composition function. I have shown you how to find out the composition function and what will be the domain and codomain. So after that, we were discussing about the lemma. What is a lemma? If alpha is a curve in a surface M whose root lies in the image x of D of a single patch x, then there exists a differentiable functions a1 and a2 such that alpha of t is equals to x of a1 a2 a1 of t a2 of t. In the last lecture, I have shown you on the board how these functions exist and what is a codomain and codomain, how the x inverse is defined, what will be x inverse of alpha. These we have studied in the last lecture. I have shown you in detail on the board itself that how the function is defined. This figure I have already shown you. So what is the x? X is a function from D to N. This is already known to you. What is alpha? Alpha is a one curve. So if it is a curve, it must be a function from open interval I to E3. Instead of E3, it is on a surface M. Okay. So now what will be x inverse? It will be function from x of D to D. So what will be x inverse of alpha? It will be function from I to D. So open interval I to D. So this will be x inverse of alpha. So now since alpha is differentiable, what we know alpha is differentiable because we know that the curve alpha is a what is given to us a curve alpha. Alpha is a curve whose alpha is a curve in a surface M whose root lies in the image x of D of a single patch, and there exists a unique differentiable functions a1 a2 such that. Okay, now here this will be the question for everyone that since alpha is differentiable, so who know that alpha is a differentiable, whether it is given that alpha is differentiable at every point. So next it is written that x inverse of alpha is also differentiable. In the I hope you are seeing the lectures, so it will be come to know to me that if up to tomorrow, that is up to 12 December, अगर आप में से किसी ने 12 दिसंबर को मुझे रिप्लाई किया तो समझ में आएगा कि आप लोग रेगुलरली लेक्चर देखते हो, राइट? सो जस्ट टेल मी व्हाट विल बी x इनवर्स ऑफ अल्फा. What will be the condition for being x inverse of alpha is a differentiable? Because alpha is differentiable, it is not given to us. So are you going to assume alpha is a differentiable and with the help of that we are saying that x inverse composition of alpha is a differentiable. So if they are differentiable, that is a question for you. So finally we will assume that let a1 a2 be the sum function, that is x inverse of alpha is a function from I to D. So in this way, if it is in D, so it is a in R2 space, so it will be consisting of two variables that we will write down a1, a2, t. So x inverse of alpha of t is equals to, it is a function from I to D, so that's why from interval I we can take a t. Okay, x inverse of alpha is equals to a1 of t, a2 of t. So in the next, x inverse of alpha is equals to a1, a2. So as t is arbitrary, we can write. So hence alpha is equals to, we can write. Because if you multiply by x on both sides, we can get alpha is equals to x of a1, a2. So on the next further, we can have alpha is equals to x of v1, v2, where v1, v2 are differentiable function. That means here we are going to assume the contradiction because we have to prove the uniqueness. Here we have shown the existence of this alpha is equals to x of a1, a2. That means there exists some functions a1 and a2 which are differentiable function which satisfy the condition alpha is equal to x of a1, a2. But we have to prove the uniqueness also. So to prove uniqueness, let us assume the contradiction alpha is equals to x of v1, v2. So that means we will assume that there exists some another differentiable functions b1 and b2 which satisfy the same condition. So now what is a1 a2 is equals to, we have written here this a1 a2 is equal to x inverse of alpha. That is, what is alpha we have now? This is x of v1 b2. So instead of having alpha here, we have written x of v1 b2. So now x inverse will be nothing but identity. So here we get a1 a2 is equals to b1 b2. By coordinate wise equality, we can get a1 is equal to b1 and a2 is equals to b2. So hence we can say that a1 a2 are the unique functions. Okay. So in this way we have covered this lemma. Now before going to next one, we must know what is a tangent vector, normal vector, all these things what we have studied in our differential geometry up to now. From the first chapter we have studied what is a tangent vector, what is a normal. Normal means it is a perpendicular to every tangent vector on the surface M or the on the curve. Okay. So now we are going to study what is a tangent vector on the surface M. So tangent vector on the surface M, it is equivalent to say that it must be tangent to at least one curve. Because if you go back to our patch computation, how the surface is constructed? The surface is constructed with the help of, if you remember, we have studied what is a patch computation. So how you are going to find out a surface, or suppose if you want to find out, suppose you want to study that geographical patch that we have studied in the lecture, that how to find out the geographical patch. Okay, I hope it is somewhere here. So this is what a patch computation is. Okay. So in this patch computation, see clearly that every straight line is converted into a curve. So with the help of all those curve, we are going to construct a surface. So what is surface? Surface is simply collection of the curve but in particular manner. So these straight lines is converted into the curve, that is u parameter or v parameter curve, which is called u parameter in which v is a constant, which is called v parameter curve in which u is a constant. Okay. So with the help of this, you can see. So we were discussing about the tangent and normal vectors, right? So what is a tangent vector? Let P be the point on the surface M. Tangent vector to M V. Tangent vector V to E3 at a point P is a tangent to the surface M if E is a velocity vector to some curve in a surface M. If you remember in the last point of the chapter first, we have studied what is a vector for the curve. If you are having a curve, then how to find out the tangent vector to the curve. Tangent vector to the curve is nothing but the velocity vector. Those who remember, those who have studied the first chapter, they can understand this why velocity vector is a tangent to the curve. So if I want to find out the tangent vector to the surface, it is equivalent to find out the tangent vector on the curve. And what is a tangent vector on a curve or to the curve is nothing but our velocity vector. And how to find out a velocity vector? Just you have to differentiate a given curve alpha. That is, you have find out the derivative of a curve alpha with respect to a variable t. So if P is a point on the surface M, if you want to find out a tangent vector to at that point, so it is equivalent to say that V is a velocity vector of a some curve in a M. The set of all tangent vector to the surface M at a point P is called a tangent plane of a M at a point P, and it is denoted by TPM. Those who remember, we have studied that tangent space. What is a tangent space at a point P is nothing but the collection of all the tangent vector at every point P of a E3 space. So instead of having E3 here, we have written a surface M. So we have just restricted our domain. That is, instead of having the tangent vector at every point of the E3 space, we have specified a tangent vector to simply on the surface M. So we have to find out the tangent vector at every point of the surface M. The set of all tangent vector to the surface M at a point P is called a tangent plane or tangent space, we can call. No doubt, as we are restricting this to a point P, so at every point P you can find out a tangent space. So you can remember we have studied that at every point of a surface, at every point of a E3 space, we can find out a collection of all the tangent vector at a point P, and those collection is called a tangent space. So here those collection for a point P of a surface M, instead of a E3, it is restricted to a surface M. This is called a tangent plane. Okay. So tangent plane is to so here you can see at every point P you can find out many number of tangent vector, and this is called a tangent plane. Okay. Now this lemma is very important for us. Let P be the any point of a surface M in E3, and let X be the patch in a surface M such that X of U naught V naught is equals to P. A vector V of E3 at a point P is tangent to the surface M if and only if V can be written as linear combinations of XU, U1, U naught, V naught, and XV, U naught, V naught. Correct? So what is a theorem? What is a lemma tells us? Let P be the point on a surface M. P is any point on a surface M given to us. And let X be a patch. That means we are provided that X is 1, 1 and regular. Such that what is the condition for a point U naught, V naught? For any point U naught, V naught, X of U naught, V naught is a that point P which we have assumed. A vector V of E3. Okay, any vector V of E3 at a point P is tangent to the surface M. Okay. What we have to prove, vector V is tangent to the surface M at a point P if and only if V can be written as linear combinations of XU, U naught V naught, XV, U naught V. Correct? Now, if I hope you are knowing about how to find out basis to any vector space. How to find out a basis? What is the meaning of basis? That means basis is nothing but the linearly independent set, and it is going to span the set. And spanning condition we can remove if you are having if you are discussing on a finite dimensional space. And here in the differential geometry, complete discussion is depending on the E3 space. So hence we are assuming that what is a use of basis will be known to you. Okay. So what is a basis? That means if any vector you are having, that vector you can write down in the linear combinations of the basis vector. Correct. So if you remember, we have studied that mapping X is said to be regular if and only if XU cross XV is not equal to 0. This theorem we have proved. And it is very similar to the curve alpha is said to be regular curve if alpha dash of t is not equal to 0. In the very similar way, we have XU cross XV not equal to 0, as X is a with two variable u and v, hence we are finding the derivative with respect to both the variable. And if the curve alpha is with a single variable t, hence alpha dash of t is not equal to 0, ensures that the curve alpha is a regular curve. Okay. So now we have to say that any vector v can be written as a linear combinations of xu and xv. So in this part, we have to just prove that xu and xv are nothing but the basis vector. That means any vector v can be written as a linear combinations of the basis vector. Okay. So these are the things provided to us, and we have to prove that v is can be written as a linear combination of the xu and xv. Okay, so let us start with the proof. First, we are provided with v is a tangent vector to the surface M at a point P. So there should exist alpha of 0 is equal to some point P. Right, some at initial point it will be some point P. So as we are provided, let P be the any point on the surface M in the initial statement. Let X be the patch such that X of U naught V naught is equals to P. So that's why we have assumed alpha of 0 is equal to P. So what is a vector? Now instead of taking any vector, we will take a vector which we know already. Okay, as we are having any vector in E3 space. So out of all those vector, we will select one vector which we know. What is a vector which we know is alpha dash of 0 is equals to V. Right? Why? Because we know that what is a tangent vector or to the surface. Here you have studied what is a tangent vector to the surface is it is nothing but a tangent vector or the velocity vector to the curve in the surface M. Okay, how to find out the velocity vector to the curve in a surface M? It is nothing but your alpha dash of t. Okay, so if it is a velocity vector to the curve, it is nothing but the tangent vector to the surface M. Okay. So in this way, alpha dash of 0 is equals to v, as it is considered at u naught v naught. So hence we are taking the initial points. Okay. So by the last lemma, what we have, if a alpha is a curve in a surface M and X is a path, then there exists a unique differentiable functions A1 and A2 such that alpha can be written as X of A1, A2. Okay. So with the help of that lemma which we have studied last one, that is alpha of t is equals to X of A1, A2, A1 of t, A2 of t. Now if you differentiate, how to differentiate this, as it is a function of X is a function of t. So we have to now use a partial derivative. Okay. So what is a partial derivative? Dou x by dou u du by dt. Dou x by dou v du dv by dt. Now as you know that what is du by dt? U is nothing but your a1 of t. What is v? V is nothing but a2 of t. So now directly you can find out a derivative d of a1 because a1 a2 are some differentiable functions. Okay, so what is a partial derivative of x with respect to u is xu and xv. Now simply if you see here, we have written alpha dash of t as linear combinations of xu and xv, but now we have to prove this dA1 by dt and dA2 by dt as a constant. Then we can prove the result. So for that, what we have done, alpha dash of, instead of t, we have assumed alpha dash of 0. Okay, so for that, let me first find out what is alpha of 0. That will be our point P, that is our assumption. That is x of a1 of 0, a2 of 0. That is nothing but u naught and v naught, correct? Because a2 of a1, a2 we have assumed as a u and v respectively. So now what we have to do, alpha dash of t. So whatever the equation we have found here, in this equation we have to put t equal to 0. After putting t equal to 0, what we can get, as a1, a2 are nothing but some differentiable functions, what will be the value of those functions evaluated at t equal to 0? It will be some constant now, because a1, a2 are functions of t, and then if you put t equal to 0, that may be directly 0, it may be some constant. So hence we have proved that any vector v can be now written as a linear combinations of xu and xv. Okay. Now in the reverse part, what you have to do, we have provided that a tangent vector v is written as a linear combinations of xu and xv. So what we have to prove now, in the second part, we have to prove that v is a tangent vector to the surface M. Okay, so in the second part, we have assumed that let v be a let v be a tangent vector to E3, and it is written as v is equal to C1 x x. That means v is a tangent vector which is written as a linear combinations of xu and xv. So as it is a linear combination, C1, C2 are some constant. So we let us define a curve alpha of t is equal to x of, instead of defining some another function, we have defined a u naught of u naught plus tc1, v naught plus tc2. That is nothing but, instead of taking any curve, what is a1, a2, these are some functions of t. Instead of taking any some another function, we have taken a simply a straight lines. Okay, straight line is also one function or one curve. Okay, what are a1, a2? So let me go back. What we have to prove, v be a tangent vector to the surface M, if and only v can be written as a linear combination. Now we have to prove that v is a tangent vector to the surface M. In the second part, if v is a tangent vector to E3, we have assumed. Now what we have to do, alpha is a curve which is defined by, instead of taking any curve alpha, we have taken a straight line. Okay, what is the equation of a straight line? Some constant p plus tq. Instead of p and q, we have a some another constant u naught and u naught c1, v naught c2. Okay, so alpha is a curve in a surface and such that now if we put t equal to 0, we can get a directly our point that we have provided. Alpha of 0 is equal to x of u naught v naught, that is equals to a given point p. Differentiating alpha. So if you differentiate a curve alpha, so you can get dou x by dou u. So what is the derivative of u with respect to t? That is derivative u naught plus t c1. With respect to t, it will be simply c1. With respect to v, the derivative of this term with respect to t is equals to, it will be simply c2 because v naught and c2 both are constant term. Okay, so hence now we can have this alpha dash of t is equals to c1 xu u naught plus t c1 v naught plus t c2 plus c2 xv is u naught t c1 v naught plus t c2. Okay, now if I put t equal to 0, because all the discussion is on the initial point, so finally you can get alpha dash of 0 is equals to. So what is the value of this term we have assumed? If you go back, we can have alpha dash of 0 is equals to is nothing but C1, this is nothing but your vector, tangent vector V, correct? So what is a tangent vector V? This is nothing but C1 XU, U naught V naught, C2 HU, U naught V naught. So this alpha dash of 0 we have is nothing but a tangent vector V. So this alpha dash is nothing but the velocity vector, right? With the help of a curve alpha. If a curve alpha is given to you, you can find out the velocity vector. So as this curve alpha is in a surface M, so it will be a tangent vector to the surface M. Okay. So V is a velocity vector of a curve alpha as curve alpha is in a surface M. So how to find out an tangent vector to the surface M? It is equivalent to find out a velocity vector to the curve alpha or the tangent vector to the curve alpha, because velocity vector, tangent vector both are same for the curve alpha. For any curve alpha, how to you can find out a tangent vector or velocity vector at every point of the curve alpha. That is just differentiate alpha dash of t, you will get the velocity vector. And hence, by definition of a tangent vector to the surface M, V is a tangent vector to the surface M. And hence the proof. Okay. So now in the next part, we will prove that but we have a tangent vector ZP at a point P. That is, what is the definition? Euclidean vector field Z on a surface M in E3 is a function that assigns to each point P of surface M a tangent vector Z of P at a point P. Okay, these are some definitions. Euclidean vector field V on a Z for which each tangent vector Vp is a tangent to the surface M at a point P is called a tangent vector field on a surface M. Okay, these definitions are very similar to our definitions of vector field. What is a vector field? Vector field is nothing but the collection of all the tangent vector at every point P of a surface M. Every point P of a E3 space. But now we have restricted this to a surface M. Okay, so Euclidean vector field for a surface M is a nothing but at every point P of a surface M, if we collect a tangent vector, that will become a tangent vector field. Okay, you have a doubt, you can ask me. A Euclidean vector field Z at a point P of a surface M is normal to surface M if it is orthogonal to tangent plane. This is a definition for the normal to the surface M. Normal to the surface means what? It is normal to every tangent vector on the surface M. So now if I want to find out a normal to the surface, it is equivalent to find out the normal to the tangent plane, correct? So Euclidean vector Z at a point P of a surface M is said to be normal to the surface M if it is orthogonal to the tangent plane M. Right, first you have to find out a tangent plane. So normal to the tangent plane will prove that it is normal to every point on the every tangent vector on the tangent plane. Right, these are the things I am not taking in detail because already we have covered these definitions in our first chapter. What is a tangent vector, vector field, and what is a normal vector. So if you have any type of a doubt, you can ask. बस हमने डिफरेंस क्या किया है, वहाँ पे हमने सब E3 पे स्टडी किया है, यहाँ पे हम सिर्फ M पे डिस्कस कर रहे हैं. So we have just taken a domain as a M. So instead of having a domain as whole E3 space, we have restricted our domain to a surface M. Okay. So now let us go for the next point. What is the next point? If we have the D is equal to C is a surface given to us, so we have to find out a gradient vector field. Okay. So what will be the vector field or a gradient vector field? It is if it is a gradient vector field or tangent vector field. So how to find out a tangent vector field? It is very easy to find out tangent vector field if you know the normal vector. Okay. Normal vector means what? It is perpendicular to a tangent. That means if you have a normal and tangent, then product of these two should be equals to 0. Correct? So if G is equal to C is a surface given to us, if it is a surface, obviously you can know that dg is not equal to 0. So now we have to find out whether this is a gradient vector field. We have to show that this is a gradient vector field. To show this is a gradient vector field, we have to find out a normal vector. And we have to show that the product of these two is equal to 0. Okay. So is a non-vanishing normal vector field. Sorry, we have to prove this as a normal vector field. Then the gradient vector field defined on a surface M is a non-vanishing normal vector field. So as it is a normal vector field, we have to find out a tangent vector. So product of these two should be equal to 0. What is given to us? G equal to C is a surface given to us. Okay. So dg is not equal to 0. That is by definition of a surface. That is, we have proved one theorem that if you want to prove any geometric object to be a surface, you can directly prove that dg is not equal to 0. dg is not equal to 0 means what? All those partial derivative, that is dou g by dou x, dou g by dou y, dou g by dou z, or all are non-zero simultaneously. So we can say that dou g by dou xi are not equal to 0 simultaneously on a surface M. So what is a del G? As you know that what is how to find out a del G, if you remember, we find it is dou G by dou X, dou G by dou Y, dou G by dou Z. Those who don't remember, go back and see what is a gradient vector field or what is a gradient vector, right? So what is this? This is summation over I dou G by dou Xi ui. Okay, as we know that these are non-zero simultaneously, we can say directly del G is not equal to 0. Okay, so now what we have, G alpha is equal to C. If alpha is a curve on a surface and this curve alpha must satisfy the equation of a surface. Rather, just like we are having any point on the surface and that point must satisfy the equation. Sorry, if you are having any point on the any straight line or any curve, that point we are going to say it is point on a surface M or point on a curve only if we can say that only if that point will satisfy the equation of a curve. Okay, so in the very similar way, this curve alpha is on a surface M only if it satisfies the equation of a surface. That is, g of alpha is equal to some constant c. So now we have to differentiate this g alpha is equal to c. So what will be the differentiation? Dou g by dou a1 dA1 by dt. I have got to use a partial derivative because g is a function of alpha, alpha is a function of a t. That is, alpha is simply in terms of a1, a2, and those a1, a2, a3 are nothing but the some function of t. That is, alpha is a single variable. No? Alpha is any curve which is a function from open interval I to E3 space or surface M. So now we have to find out the partial derivatives. So here we get these partial derivatives. Now what will be V tangent vector V to the surface M? It is nothing but the velocity vector to the curve alpha. So hence V is equals to, that is nothing but V1, V2, V3. What is alpha dash? It will be nothing but these, here we have a1, a2, a3. We have to differentiate this a1, a2, a3 with respect to t. So that's why vi's are nothing but dai by dt. So in this equation, we have to replace these term with these vi. After replacing, what we can get, summation over I dou g by dou alpha dou g by dou ai vi is equal to 0. So this product is equal to 0 means what? This is a vector and this if this is a vector, this should be a normal, correct? Because there is a property of a normal vector that this normal vector is always perpendicular to the tangent. Okay, so and then as it is a perpendicular, dot product of the perpendicular vector should be equal to 0. And hence, with the help of this, you can prove that del G is perpendicular to a vector V and hence it is a normal to the surface. Vector V, what is vector V? V is nothing but alpha dash of 0. What is alpha dash? Alpha dash is nothing but the velocity vector of the curve alpha. It is velocity vector of a curve alpha, means that it is velocity vector, sorry, it is a tangent vector to the surface M. Okay, because it is not possible to find out a tangent vector to the surface M, okay, directly. So we have to go to a point P, and for that point P you have a one curve, because your surface is nothing but the construction of the, that is a combination of all the curve, as you have studied in the patch computations. Okay, every single line is converted into a curve. Okay, so you have to go to a point and you have a one curve and then find out a velocity vector. Velocity vector to the curve is nothing but the tangent vector to the surface, and hence this is a tangent vector to the surface, and dot product with this term is equal to 0 means what? This should be a normal, and hence we can say del G is a normal vector. Okay. So hence, next in the next lecture we will solve the example based on the how to find out a normal and tangent vector field on the surface. Thank you.